Welcome to the lecture on queuing theory, module 4. In this module, we will develop and study two queuing models. Model 3, which is MMS infinitive FCFS, and MEK1 infinitive FCFS. In the first model, n servers or service stations are considered in parallel, and one customer can go for service to any one of the S servers or service stations if it is free, and the service time in each station or server is identical. The second model is a non-Poisson model, in which service time is considered to follow Erlang distribution with k phases. One unit is served with k phases one by one. So, let us now start our discussion on model 3, which is MMS infinitive FCFS. In this model, we assume that instead of a single server, there are S identical servers in parallel to provide service to the customers. It is assumed that only one queue is formed and customers are served on a first come first served basis by any of the servers which is free. The service times are distributed exponentially with an average of mu customers per unit time. If there are n customers in the queuing system at any point in time, then the following two cases may arise. N is less than S and n is greater than equal to S. If n is less than S, that is the number of customers in the system is less than the number of servers, then obviously there will be no queue. However, S minus n number of servers will not be busy. Therefore, the combined service rate will be mu n equal to n mu. And if n is greater than equal to S, that is the number of customers in the system is more than or equal to the number of servers, then all servers will be busy and the maximum number of customers in the queue will be n minus S. Then the combined service rate will be mu n equal to S mu. Now, this model may also be considered as a special case of model 1 general with lambda n equal to lambda for all n greater than equal to 0, and mu n can take two values, mu n equal to n mu when n is less than S and mu n equal to S mu when n is greater than equal to S. Now, we determine the probability P n of n customers in the queuing system at time t, and also we determine the values of performance measures. Proceeding similarly as in model 1, we obtain the probability that there is 0 customers in the system in time t plus delta t as p 0 t into 1 minus lambda t plus p 1 t into mu delta t plus order of delta t for n equal to 0. Similarly, for n lying between 1 and s, but not equal to s, p n t plus delta t equal to p n t into 1 minus lambda plus n mu whole into delta t plus p n minus 1 t into lambda delta t plus p n plus 1 into t whole into n plus 1 mu delta t plus order of delta t. In this expression, the first term consider the situation where there were n customers in the system. Second term consider where there were n minus 1 customers of the system, and the last term consider the situation where there are n plus 1 customers in the system. And accordingly, the services are considered, so that ultimately there are n customers in the system at time t plus delta t. Now, for n greater than equal to s, we can similarly find p n t plus delta t equal to p n t into 1 minus lambda plus s mu whole into delta t plus p n minus 1 t into lambda delta t plus p n plus 1 t into s mu delta t plus order of delta t. Subsequently, we get p 0 dash t equal to minus lambda p 0 t plus mu into p 1 t for n equal to 0, p n dash t equal to minus lambda plus n mu whole into p n t plus lambda into p n minus 1 t plus n plus 1 mu into p n plus 1 t for 1 less than equal to n less than s, and for n less than n greater than equal to s, and for n greater than equal to s, p n dash t equal to minus lambda plus s mu whole into p n t plus lambda into p n minus 1 t plus mu s into p n plus 1 t. In the steady state, the above equation reduces to minus lambda p 0 plus mu into p 1 which is equal to 0 for n equal to 0, and for 1 less than equal to n less than s, minus lambda plus n mu whole into p n plus lambda into p n minus 1 plus n plus 1 into mu into p n plus 1 equal to 0, and for n greater than equal to s, we have minus lambda plus s mu whole into p n plus lambda into p n minus 1 plus s minus into p n plus 1 is equal to 0. Applying the iterative method, the probability of n customers in the system can be obtained as p n equal to 1 by factorial n into lambda by mu whole to the power n into p 0, where n is less than s, and p n equal to 1 by factorial s into s to the power n minus s into lambda by mu whole to the power n into p 0 for n greater than equal to s. We can find the value of p 0 by using the relation sigma n equal to 0 to infinity p n equal to 1, and by simplifying we ultimately get p 0 equal to the expression which is shown in the slide. The expected number of customers waiting in the queue is L q, which is equal to summation n equal to s to infinity n minus s into p n since there are S servers, so S customers are busy in getting service. So, the expected number of customers waiting in the queue should be summation n minus s into P n, n varies from s to infinity, and putting the value of P n and simplifying, we can find the expression for L q as shown in the slide. The expected number of customers in the system, which is L s, equal to L q plus lambda by mu, and the expected waiting time of a customer in the queue, W q is equal to L q by lambda, and using the expression for L q as shown in the slide, we can further simplify W q, the expression for W q which is as shown in this slide. The expected waiting time that a customer spends in the system is W s equal to W q plus 1 by mu. The probability that all servers are busy, or the probability that an arrival has to wait, is probability of busy period, which is nothing but probability of capital W greater than 0. We can write it as probability of n greater than equal to s, and then simplifying, we can find the probability that an arrival has to wait as shown in this slide. Now, let us take an example and see how the results, the values of performance measures can be applied to solve some queuing problem. A supermarket has 2 sales girls at the sales counters. The service time for each customer is exponential with a mean of 4 minutes, and the people arrive in a Poisson fashion at the rate of 10 an hour. Then calculate the probability that a customer has to wait for service. Find the expected percentage of idle time for each sales girl, and if a customer has to wait, what would be the expected length of his waiting time. Here we are given that lambda equal to 1 by 6 per minute, and service rate mu equal to 1 by 4 per minute, number of server is equal to 2, that is s equal to 2, and traffic intensity rho equal to lambda by s mu, which is equal to 1/3. Therefore, using the expression for P 0, we can find the P 0, the value of P 0 as half and P 1 as 1/3. Now, the probability that a customer has to wait for service, that is probability of W greater than 0, or in other words probability n greater than or equal to s equal to 2, we obtained as 1 by 6, which is the probability that a customer has to wait for service. Now, the fraction of time the servers are busy is the traffic intensity rho, which is equal to lambda by s mu equal to 1/3. Therefore, the expected percentage of idle time for each sales girl is 1 minus 1/3, which is 2/3, that is 67%. The expected waiting time for a customer in the system, which is W s, is equal to W q plus 1 by mu, and if you simplify, we get Ws equal to LQ by lambda plus 1 by mu. Putting the values of LQ, lambda and mu, we finally get Ws equal to 4.5 minutes. Now, take another example. A tax consulting firm has 4 service counters in its office for receiving people who have problems and complaints about their income, wealth and sales taxes. Arrivals average 80 persons in an 8-hour service day. Each tax advisor spends an irregular amount of time serving the arrivals, which have been found to have an exponential distribution. The average service time is 20 minutes. Then we have to calculate the average number of customers in the system, the average number of customers waiting to be served, the average time a customer spends in the system, the average waiting time for a customer, and how many hours each week a tax advisor spent performing his job, and finally, what is the probability that a customer has to wait before he gets service. Here we have the arrival rate lambda equal to 10 per hour, service rate mu equal to 3 per hour, number of service stations or servers S equal to 4, traffic intensity rho equal to lambda by S mu which is equal to 5 by 6. Therefore, the probability of no customer in the system, which is P0, using this data we can easily find the value of P0 as 0.021. The average time a customer spends in the system is Ws, which is equal to Wq plus 1 by mu. Again, Wq is equal to Lq by lambda. Therefore, we get Ws as 0.657 hours, which is equal to 39.42 minutes. The average time a customer waits for service in the queue, which is Wq, and Wq equal to Lq by lambda, and putting the values of Lq and lambda, we find Wq equal to 19.44 minutes. The time spent by a tax advisor, which is nothing but the utilization factor rho, which is equal to lambda by S mu, and we obtain rho as 50 minutes. The expected time spent in servicing customers during an 8-hour day is obviously 8 into 0.833, which is equal to 6.66 hours. If the tax advisor works 5 days a week, then on average a tax advisor is busy for 6.66 into 40 by 8, which is equal to 33.3 hours. The probability that a customer has to wait, which is probability of n greater than or equal to s, is equal to 1 by factorial s into lambda by mu whole to the power s into S mu by S mu minus lambda into P0, and putting the values of all the parameters, we get the probability as 0.622. We were discussing model 3, which is MMS infinitive FCFS. In this model, S parallel servers or service stations are considered, and any customer can enter into the service station for getting service when it is free. And we have derived some results for performance measures of this model. However, until now we have developed some queuing models which can be termed as Poisson model, because the arrival and departure both follows Poisson's distribution. Now, we are going to develop and study another kind of model which is called non-Poisson model. Here we will consider the departure will follow not Poisson's distribution, but follow Erlang time distribution. Let us discuss on model 4, which is MEK1 infinitive FCFS. This model consists of single Erlang service channel in which there are k phases in series for services, each with average service time 1 by k mu. Let P and T be the probability that there are n phases in the system at time t, and n is the total number of phases in the system. Lambda n equal to lambda, which is constant arrival rate per unit time, whereas mu n equal to k mu phases served per unit time. Since each customer is served in k phases 1 by 1 and a new service does not start until all k phases have been completed, therefore, each arrival increases the number of phases by k in the system. Thus, if there are m customers waiting in the queue and one customer is already in service at sth phase, then the total number of phases in the system n equal to mk plus s. Using the same procedure as discussed in earlier models, we obtain P0 t plus delta t equal to P0 t into 1 minus lambda delta t plus P1 t into k mu delta t plus order of delta t for n equal to 0. And for n greater than equal to 1, P n t plus delta t equal to P n t into 1 minus lambda plus k mu whole into delta t plus P n minus k t into lambda delta t plus P n plus 1 t into k mu into delta t plus order of delta t. Transforming these equations into the system of differential equations, we get P0 dash t equal to minus lambda P0 t plus k mu into P1 t for n equal to 0, and P n dash t is equal to minus lambda plus k mu whole into P n t plus lambda into P n minus k t plus k mu into P n plus 1 t for n greater than equal to 1. This system of equations give rise to the following system of steady state difference equations. For n equal to 0, we get lambda P1 equal to rho into P0, and for n greater than equal to 1, we get 1 plus rho into Pn, which is equal to Pn plus 1 plus rho into Pn minus k, where rho is equal to lambda by k mu and P0 equal to 1 minus rho k. Now, the expected number of phases not customers in the system can be obtained from this model as LSK, which is equal to k plus 1 by 2 into lambda by mu minus k, and then LQK, the expected number of phases in the queue, which can be obtained as LS k by mu, which is equal to k plus 1 by 2 into lambda by mu into mu minus lambda. The expected number of customers, but not phases in the queue LQK can be obtained as LSQ minus average number of phases in service by k, and here since 1 by mu is the average service time per customer, k plus 1 by 2 is the average number of phases of one customer in service. Therefore, the time taken for servicing a customer will be k plus 1 by 2 mu. Thus, the average number of phases that arrive in this time would be lambda into k plus 1 by 2 mu. Using this result and simplifying, we can finally obtain LQK is equal to k plus 1 by 2k into lambda square by mu into mu minus lambda. The expected waiting time of a customer in the queue, which is WQ is equal to LQ by lambda. Since we know the value of lambda q, we can find the value of WQ as k plus 1 by 2k into lambda by mu into mu minus lambda. The expected waiting time of a customer in the system, Ws equal to Wq plus 1 by mu. Putting the value of Wq, we find the value of Ws as k plus 1 by 2k into lambda by mu into mu minus lambda plus 1 by mu. The expected number of customers in the system, which is Ls, equal to Lq plus lambda by mu, and here we put the value of Lq and simplify, we get Ls equal to lambda into Ws. Now, let us consider an example and see how the results of this non-Poisson queuing model can be applied to find the solution of the queuing problem. A hospital clinic has a doctor examining every patient brought in for a general checkup. The doctor averages 4 minutes on each phase of the checkup, although the distribution of time spent on each phase is approximately exponential. If each patient goes through 4 phases in the checkup, and if the arrival of the patient to the doctor's clinic is approximately Poisson at an average rate of 3 per hour, then to determine the average time spent in the examination, and also we have to determine the most probable time spent in examination. Here the number of phases k equal to 4, the mean service time 1 by mu is equal to 16 minutes, and mean inter arrival time 1 by lambda is equal to 20 minutes. Therefore, the average time spent in doctor's clinic is Wq equal to k plus 1 by 2k into lambda by mu into mu minus lambda, and putting the values of k and mu and lambda, we get Wq equal to 40 minutes. In order to find the most probable time in the examination, we have to find the modal value of t for the hour-length service time distribution. The PDF of hour-length service time distribution is given by St mu k is equal to e to the power minus k mu t by factorial k minus 1 into k mu whole to the power k into t to the power k plus 1, where k is greater than or equal to 1 and t takes finite value. Now, the first derivative of s with respect to t equal to 0 yields t equal to k minus 1 by k mu, and since the second derivative is less than 0 for t equal to k minus 1 by k mu, we can say that the mode lies at t equal to k minus 1 by k mu. Therefore, the most probable time in the examination is the modal value of t, which is k minus 1 by k mu and which is equal to 12 minutes. So far in this chapter, we have developed and studied a few queuing models such as model 1, model 1 general, model 2, model 3 and model 4. The first 4 models are Poisson's model, whereas the last model is called non-Poisson model. Several other queuing models can also be developed by changing the arrival rate and service rate or queue discipline, but then the model will be complicated and it would be difficult to solve those model analytically. That is why there are several queuing models which are very much realistic, but those models cannot be solved analytically. We have to solve this model by using simulation. With these comments, we end this module as well as this chapter.